Okay, today we're going to go over concavity and points of inflection. Okay, concavity of the function f is basically when f is curving upward or downward. So if we let f be differentiable, on an open interval I, then the graph is concave up and we'll just denote that by CC and then an up arrow if f prime is increasing on an interval. And it's concave down if f prime is decreasing. So if we notice here, this graph is concave up, and if you take a point for the tangent line anywhere on this graph, f prime is increasing. Your graph is concave down, and here f prime is decreasing. Okay, so a point of inflection says if the point C comma f of C is a point of inflection of the graph of f, then either f double prime of C is equal 0, or f double prime is undefined at x equals C. Okay, so just keep in mind also that if f prime is increasing, what that implies is that f double prime is greater than 0. If f prime is decreasing, then that implies that f double prime is less than 0. Okay, so a point of inflection also describes where your graph changes from being concave up to concave down or concave down to concave up. So the point of inflection is also where your graph changes concavity. So it either goes from being concave up to concave down, or from concave down to concave up. So an example would be the graph of sine. So we know sine does this. Okay. So here, your graph is concave down. At this point, it starts becoming concave up. So a point of inflection would be this point here at x equals pi. So how do we test for concavity? Okay, so we're going to say let f be a function whose second derivative exists on an open interval. So on some open interval I, then then if f double prime of x is greater than 0, there exists an x in I then the graph of f is concave up in I. Similarly, if f double prime of x is less than 0, then for all x in I, then the graph of f is concave down. All right, let's go ahead and take a look at an example. Okay, so example. Find the points of inflection and discuss the concavity of the graph of the function. Okay, so here our function is f of x is equal x to the fourth minus 4x cubed. Okay, so first thing we need to do is we need to take the derivative, the first derivative. So f prime of x is equal to 4x cubed minus 12x squared. And now we take our second derivative. F double prime of x is equal to 12x squared minus 24x. Okay, so now we want to look for possible points of inflection. So our possible points of inflection are when f double prime of x is equal to 0, or f double prime of x is undefined. Okay, so because this is a polynomial, it's always going to be defined. So now we just focus on when f double prime of x is equal to 0. So let's go ahead and set f double prime of x equal to 0, and we end up with 12x squared minus 24x is equal to 0. Well, we can factor out a 12x, we get x minus 2, that's equal to 0. So we have possible points of inflection at x equals 0 and x equal 2. So the same that we did with our sign chart, let's go ahead and try that here, except for this time we're going to use f double prime. Okay, so possible points of inflection are at 0 and 2. So here up top we put f double prime. So if f double prime, so let's go over this again. If f double prime is greater than 0, your graph is concave up. If f double prime is less than 0, your graph is concave down. So we want to choose test values. So here, if we choose test values of, here, let's go x equals -1, x equals 1, and how about x equals 3? And again, all we're worried about are the signs. So if f equals -1, f double prime of -1, so we do plug this into the second derivative. We already have it factored here, and all we're looking for is whether it's positive or negative. So at -1, 12 times -1 is a negative. -1 minus 2 is a negative. So we get a negative times a negative, so that is a positive. Okay, so that means that from -infinity to 0, f is concave up. From 0 to 2, we have a test value of 1. So 12 times 1 is a positive. 1 minus 2 is a negative. Positive times a negative is a negative. So from 0 to 2, the graph of f is concave down. Okay, and finally, we have a test value of 3. 12 times 3 is positive. 3 minus 2 is positive. Positive times a positive is positive. So from 2 to infinity, f is concave up. Okay, so how do we write this out? All right, so f is concave up on the intervals from -infinity to 0 and the interval from 2 to infinity, since f double prime is greater than 0 on these intervals. F is concave down on the interval from 0 to 2, since f double prime is less than 0 on the interval from 0 to 2. All right, so this tells us where we have our function is concave up, concave down. How about the points of inflection? How does that work? Okay, so again, we said a point of inflection occurs where your graph changes concavity. So where does our graph change concavity? So here, f has points of inflection at x equals 0 and x equal 2, since f double prime changes from positive to negative at x equals 0, and from negative to positive at x equals 2. Okay, so there we have our change in concavity. Okay, so that'll do it, and good luck on the homework.